Okay, good morning. Welcome, everybody. Thank you for taking time out of your day to check out this introduction to concrete scanning. Thank you to those who are missing the kickoff of Brazil-Serbia to watch this. I appreciate that. So my name is Mike. I have worked for Xradar for around 10 years. I've been in the industry. This is my 10th year. I joined Geoscan in 2013. Specialized in using GPR for concrete surveys, utility surveys, geophysical surveys. I've worked for both Geoscan and Xradar, and I've moved full-time to Xradar a few years ago. My focus these days is on structural investigations, as well as non-destructive testing surveys, which involves corrosion surveys and void surveys. If you have any questions, please type them into the Q&A box, and we will answer them at the end of the webinar. So what are we going to cover today? We're going to look at what is Xradar. We're going to look at concrete scanning methods in the industry. We're going to look at how it works, issues in the industry, training in the industry, scanning comparisons, data comparisons, reporting, and any additional services. So what is Xradar? We are primarily concrete scanning and imaging company. We do concrete scanning, concrete coring, structural surveys, corrosion surveys, and void surveys. Core values are community, excellence, innovation, and honesty. Community, because we believe our team is our biggest asset. Excellence, because we strive to be the best in what we do. Innovation, we're always improving methods, technology to push the industry forward, often trying to give clients things they don't know they need yet. And honesty, because we strive to be fair and honest in everything we do. We have locations in Montreal, Vancouver, Toronto, Quebec City, Ottawa, and recently Kuala Lumpur. So current concrete scanning methods in the industry. X-ray is a method that's been around for a long time. Ground penetrating radar is a little bit more modern. And more recently, Xradar. So let's take it back. X-ray is the oldest and probably most established method for imaging concrete. It's pretty outdated these days. However, it does work in a very similar way to the medical industry. It gives you an internal image of the slab. Therefore, it can be pretty useful. It's very detailed. You can see individual ribs on pieces of rebar, for example. However, it has many drawbacks. In order to X-ray a slab, you need access to both sides of the slab. That isn't always possible. It completely eradicates slab on grade out of the picture. The max depth for imaging with X-ray is around 12 to 14 inches. And anything bigger than that, the exposure time is just too long. X-ray struggles with finding plastic conduits at depth. And it also has no concept of depth of targets. So you can see what's there, but you have no idea necessarily how deep they are. One of the biggest problems with X-ray is obviously it's radioactive. You must evacuate everyone when you do it, which usually means doing the work at nighttime or double the cost for the client, essentially. The other large issue with it is it's a fixed location image. If you spend your money and spend your time taking your shot, and then there's a lot of conduits in the way and you can't put your hole there, you then have to just move and pick a new spot and start the process all again. So there's no real in-time live idea of what is going on until you look at the information. Ground penetrating radar. Now I'll get into how GPR works shortly, but regular GPR units are about in the industry today, and they can determine simple rebar patterns. GPR's main advantage over X-ray is that it collects data in real time. So there's no waiting for shots. You can see live if an area is busy or not busy. And in part, you can then move to an area that isn't busy and spend your time working on that area. The only problem is the current industry, these units have been dumbed down for mass production, essentially made to be a lot easier in order to sell these units to the general public. So these units cannot distinguish conduit from rebar. They cannot identify conduits hidden below rebar. They struggle to determine bar size. They struggle with multiple layers of rebar. The biggest issue with ground penetrating radar is it's an interpretive technology. The live data must be analyzed by an experienced and properly trained technician. So unfortunately, manufacturers have chosen to produce these really easy to use units with limited capabilities and essentially just trying to appeal to the mass market. The current industry error rate using these regular units is approximately 25%. So that would account to missing 1 in 4 conduits, essentially. Xradar is essentially as accurate as X-ray, but is as efficient and safe as GPR. Xradar utilizes ground penetrating radar, but it utilizes high-end units of high-frequency antennas. These antennas have been slightly modified and developed further in-house, basically in order to maximize its potential. The most important factor in here is combining it with rigorous training. And as a result, Xradar can map out complex rebar maps. It can determine targets hidden under other targets. It can determine slab thickenings, layer changes, can identify material changes, for example, plastic versus metal, i.e. a conduit versus a rebar. Target type, even if they're the same material, can be determined. Post-tension cables versus rebar. Diameter of targets can be achieved to a certain extent as well. The current industry success rate using Xradar is 99.7%. So, how does GPR work? And this is why we're here today. There are different setups depending on what equipment you use, but there's always a screen and there's always an antenna. The antenna will contain a survey wheel which has an encoder in it, and this is essentially how the antenna knows its position on the surface. The first and fundamental thing to understand is about radar is essentially radar will travel through different materials at different speeds. This is the basis of how GPR works. So radar pulses will emit from the antenna into the concrete, and when they hit something with a change of density or changing dielectric properties, it will rebound and be received by the antenna. The greater in contrast between the two properties of the two materials will result in the greater the reflection. For example, metal inside concrete are very two contrasting materials. So it's very, very easy to see it. The reflection is very strong. The amplitude of that reflection is very high. The difference between plastic and concrete is still very contrasting, but it's a little bit closer than metal and concrete. Therefore, the reflection is a little bit weaker, but it's still prominent. How something reflects is a direct product of whether the radar slows down or speeds up upon hitting that new material. One thing to really, really take into account is conductivity. Conductivity plays a huge part. The more conductive a material is, the slower the radar will travel. Metal is obviously very conductive, therefore radar will not travel through it at all. And it fully reflects from metal, which is in turn why metal is so easy to see. Here's a fun historical fact. Back in the 1950s and 60s, US Air Force pilots were using radar for altitude measurements over Arctic ice. 4 or 5 of the planes crashed into the ice. And the reason for that was the radar was going through the ice and hitting the bedrock and coming back. So altitude readings were completely incorrect. When they thought they were 100 feet off the ground, in fact, they were not 100 feet off the ground. And this is when they realized that radar actually travels through materials. It doesn't just bounce off them. This is a quick diagram of how an antenna would move across a surface. As it moves across, it starts to pick up targets in the surface. This is a piece of rebar, and it creates a hyperbola. The way it figures out how deep it is essentially the time it takes for the radar wave to travel down, hit the target, and come back. The only factor the machine doesn't know is the speed at which it's going to travel, because as we suggested earlier, it travels at different speeds through different materials. Therefore, calibration is crucial. By telling the machine what velocity the radar will travel, i.e. what material you're scanning, you can get accurate depth to targets. And this is a really, really important factor that needs to be understood. So what does it look like? This is a typical radargram. And this is a very, very simple suspended slab. You've got 2 layers of rebar. And what we see is a profile view of the slab. So this is the surface. As you run across the slab with your antenna, you see these hyperbolas in the slab. So the green is rebar in the top of the slab, top rebar. Blue is rebar at the bottom of the slab. Obviously, you can see the bottom rebar is deeper than the top rebar. The yellow line is essentially the bottom of the slab. So the radar has traveled through the slab and it's hit the air, and it's actually sped up because it travels through air quicker than it travels through anything else. So you get this nice consistent line at the bottom, and that indicates the bottom of the slab. In this case, approximately 8-9 inches, something like that. This one here has been misled, and it's actually a conduit. Given the spacing of the bottom rebar, to me, in my experience, I would say that is an electrical conduit running through the slab. So it's very easy to get misled sometimes, and why you need to understand what you're looking at. This is a lot more complicated image. It'd be very nice if every image was like this, but it's not. Here you've got multiple layers of rebar. I can't see the bottom of the slab at all. Below the rebar, you've got post-tension cables running through the middle of the slab. The top half shows an image from a regular GPR, and you can see how the post-tension cables are almost shielded by the rebar above it. When scanning using Xradar technology, we're able to highlight this information below and actually see stuff that is essentially shielded before. So it's a lot more conclusive. Here's a quick example of slab on grade. So obviously slab on grade means slab on the ground. There's no rebar in this at all. The idea is the ground is holding it up. So again, we've got our bottom of the slab line. However, it's pretty uneven. It's not as straight as a suspended slab because the ground is not perfectly straight. You've got gravel and subgrade below. So you get an uneven bottom of the slab. You also get reflections from the soil and the subgrade. It's not as clear. The radar is not heading into air. It's now heading into the ground. So we're still imaging the ground. And you can even make out pipes below the slab. This is a plastic plumbing pipe below the slab. So what are the issues in the industry? Or the areas of concern? Choice of equipment. Concrete scanning is an unregulated industry. Anyone can go out and buy a machine, but do they know what they're doing, essentially? And as I suggested earlier, the manufacturers have chosen to dumb down these units for the mass market. They want to sell as many of these products as they can. And in reality, GPR's greatest strength is when you have a highly trained operator who can interpret complex data it provides. If you look at the medical industry, for example, you wouldn't have a machine tell you whether you've broken your arm or not from the X-ray. You'd have a trained professional looking at the X-ray and making those judgments, understanding that it's not just a black or white situation. The other monumental issue with the industry is the lack of training. Because it's unregulated, the current standard is a 2-day course provided by an equipment manufacturer, essentially, which is nowhere near enough. Understanding ground penetrating radar requires a lot of experience, a lot of training. Not only must you learn about geophysics and the science behind how the equipment and radar works, but the scanning environment is crucial. For example, you may be a geophysics PhD, but if you know nothing about structural slabs or concrete, then you'll be completely lost. Xradar training scheme takes around 9 months to a year before someone is considered qualified to go out on their own. And then that is essentially the start. From there on, you progress with more and more complex jobs, more complex slabs, and it's only ever evolving in experience. Another byproduct of the unregulated industry is essentially the lack of accountability. There's a huge tendency to blame the equipment when things go wrong. Contractor comes in, they scan, they hit a conduit. This useless piece of equipment, it should tell me where everything is. And that's completely misunderstanding the point. You need to have people who are experienced in order to understand what you're looking at. People are very easy to wash their hands of responsibility. As you all may know, assuming a lot of you are in the Canadian construction industry, everyone in the construction industry is in a big rush. It moves very fast. Everyone wants to finish their projects or their part of the project, and there's a lot of corner cutting sometimes. These quotes are stuff I hear regularly on a daily basis. A lot of people assume they know. There should be nothing there. In reality, they don't know. Post-tension is an increasingly big problem. Given the sort of Vancouver area being in a seismic region, buildings are increasingly more reinforced, increasingly more stringent on what you can and can't cut in terms of structural rebar. Post-tension cables should never be cut. And there's more and more post-tension buildings in Vancouver than I've ever seen. And it's becoming a big issue. This photo here actually shows some post-tension cables less than half an inch from the surface of the concrete. So when you're anchoring inserts into a slab, huge issue. There's a lack of kind of acceptance of avoiding rebar. A lot of people, they want to get their job done. They want to just core a hole. This has 6 35mm bars without structural approval. The building may not fall down, but if this happens consecutively over the next 10 years, various, TIs, various kind of revamps of the building, that integrity gets lost pretty quickly. And so it's an increasingly big problem. This photo I actually took myself. This was on a site. They were anchoring in the ceiling to hang a plumbing line. Post-tension cables were lying less than an inch from the surface of the concrete, drilled right into it. And I don't know how much everyone knows about post-tension cables, but they're under very, very high tension. The minute you cut it, it will blow out the end of the cable. And it's not only dangerous, but it's very bad for the structural integrity of the slab. So training is absolutely crucial. We focus a lot of our time on training technicians and helping them understand the science behind it and the environment they're scanning. They go through, as I said earlier, it's up to a year usually before they're graduated, and this involves theory. It involves scanning on site, shadowing people, gaining that experience, and also involves auditing, testing them, making sure that they're making the right decisions. And honestly, the hardest bit is the decision making. You may be able to scan it, you may be able to see everything there, but it's deciding what to do or what decision to make in that situation. And that really does take time. Now, nothing is without limitations. And the biggest problem is we understand the limitations, but not necessarily do the clients understand the limitations. They expect you to come and just magically be able to see everything that's there. And it's not always the case. So depth is obviously a huge limitation. Radar attenuates at depth. So radar essentially loses energy. So depth of penetration depends on the age of the slab and what's in it. So as we talked about earlier, conductivity is huge. So a new slab is a wetter slab, which is more conductive. So radar penetration is a lot poorer. Typically, we can scan between depths of 12 to 16 inches from one side. Therefore, scanning from both sides, you can gain up to 24 to 32 inches. And again, depends on the age of the slab. The older the slab, the better and further you will see. Tight rebar is still a huge problem. As we said earlier, radar does not travel through metal. Even with enhanced Xradar technologies, we're able to see past certain things and see things hiding below. However, when the rebar is really, really densely packed together, it creates a shield, and it's almost like someone has closed the blinds. Not much of that light is getting through, and you're unable to see what's below. Now, in my experience, everyone wants to core holes next to columns. It's a nice, tidy place to hide a pipe, but it's also the place with the most rebar. Same next to slab bands, the most rebar. Don't forget, you can scan both sides of a slab, and often this is the approach that's needed in order to clear these busy locations. A big one is obstructions. often you're presented with a tiny little area in a crawl space and just said, this is where I want to put my hole. Now, you really do need a minimum of a 2x2, if not, the bigger the better. You really need that space to understand the spacing and the layout of the slab. You have to physically be able to go over a target in order to mark it in. So we cannot safely scan within 2.5 inches of an obstruction. Common obstructions are like walls, track walls, strap conduits, pipes, those kind of things. And then lastly, surface conditions is a big problem. You can't scan through standing water. As we suggested earlier, water is conductive, and also the water can get into the antenna, which is no good for the antenna. The other problem is really, really rough surfaces. Anything that's really rough causes the antenna to skip. You need good coupling of the antenna and the surface in order to get good data. It's all about being prepared before you go. This is something we've kind of been doing on the side. This is a GIS database of every building we've ever been to. And within those buildings, we create records of what we found. For example, level 25 was a 10-inch slab. The rebar was spaced at this. It was 4 inches deep, etc., etc. By doing this, you have this ever-evolving record of everything you've ever done. And you're fully prepared going to sites. I'll check this before I go to every site, and I'll know, okay, I know there's post tension in this building. I may not have seen it myself, but someone else was here. They know on level 5 there was post tension. And it just sets you up for that extra layer of knowledge before you go somewhere. Accuracy. Training and equipment and preparation equals accuracy. The error rate currently with Xradar is less than 0.03%. Now, this is accounted from years of statistics we have kept based on essentially the amount of scanning we've done versus the amount of error there is. There's a 25% error using regular GPR. I'll just add the remaining error is essentially down to human error. You can never really eradicate human error. If someone's having a bad day, they forget to do something, these sort of things, they do pop up. So that is why there is a remaining 0.03%. Scanning comparison. So let's take a little look. This is a classic show up to site. Someone has scanned before, just a bunch of lines on a slab that doesn't mean anything. Whereas on the right, you have the top rebar marked in green, the bottom rebar marked in blue, electrical conduits running through the slab in red, and a boundary in yellow. Now, the boundary is actually a really important point because it differentiates what has and hasn't been scanned, which in this situation seems fairly obvious. But if you have a scan where there isn't much rebar, how do you know what the extent of what has been scanned and what hasn't been scanned? Another situation here, people were able to core a hole, avoiding the electrical conduit running through, avoiding the rebar. Again, another situation. This person attempted to mark conduits in, but they were in the wrong place. There's only one layer of rebar. In reality, there's 2 layers of rebar, pretty dense rebar in that regard. A couple of electrical conduits running through there. Sometimes when it's that heavy, people give up and they say, too hard to X-ray, too hard to scan. And for the most part, most locations can be cleared. If you know what you're doing, you have the right equipment and the right experience, you can scan most locations. So let's have a look at the data. Here's the same shot, the same profile. You can see a lot of rebar at the top. And using Xradar, you're actually able to see those hidden targets below the rebar, a lot easier than if you're using regular GPR. Now, phase change is a really, really important factor. When I talk about phase change, what I mean is the radar either slowing down or speeding up. So based on the radar slowing down or speeding up, I know what kind of material that is. I know that radar is going to slow down when it hits metal. It's going to produce a metal reflection. When it hits a plastic conduit, for example, it's going to speed up. And that actually creates a different type of reflection. and in turn helps you an understanding of what you're looking at. Now, to the untrained eye, these two images look exactly the same. On the right, I know the middle target is a conduit based on the phase change. And it takes a while to get to that point, but once you see it, you can't unsee it. Reporting. It's all very well doing a nice scan, but you've really got to present the report to a client. And the way we do that is we essentially send out a pretty instant report that contains details of everything we've done, description of the job, legend, images of each scan, the depth to each of the targets, often a floor plan that denotes the actual location of the scans within the floor plan. The reason for doing this is if an engineer needs to approve a core, if they can see the scan and the orientation of the scan, and they can see where it is on the drawing, they can determine if and what rebar may or may not be cut in this situation. And they can actually do this from their desk. They don't necessarily need to be there because they have the layout, they know the orientation, they know what they can do, what they can and can't cut. Location of the scan along with depth, any limitations that are associated with this slab. So all the information is right there. What do you do if there's no structural drawings for a building? Well, you can create them. By scanning various sections of walls or slabs, you can find the structural rebar, the orientation of it, the layout, the spacing, the diameter of the rebar, and then by creating a CAD report of this, you can present this to an engineer or a building owner, and an engineer can then use it to determine calculations, essentially. So if you don't have any structural drawings, which a lot of these buildings, they don't, they're old buildings, drawings are bad, or drawings are missing, then create your own. And this is something we're able to do by first scanning and then producing a CAD drawing of where everything is. And lastly, other areas of expertise. I'm just going to quickly dive onto some other areas that we can hit, and feel free to ask questions about these at the end. Corrosion mapping is a really, really useful tool. Concrete structures obviously corrode over time, and concrete mapping is an extremely useful tool, mostly because it can be proactive and not reactive. So the ability to map something, the state of something as it is, you might determine a bridge, for example, is corroded in one area and not another area, meaning you repair that area of the bridge and you don't spend a ton of money repairing the whole bridge. And this is something we have had great success with, and is a really useful tool. Structural investigations I kind of touched on, but the ability to create a structural drawing, if it doesn't exist, an engineer can come up with load bearing capacities on something by giving them this information without any kind of destructive work. Crack and void detection is an increasingly big problem. There's two types of voids that seem to exist. One is sub-slab voids. So these are voids below slab on grade, often in warehouses and places like that. I've noticed a lot of this happening in kind of areas south of Lower Mainland. So if the ground starts to subside, you end up with this air gap between the slab and the ground. The slab cannot support itself anymore, which causes it to sink and crack, and it becomes a big, big problem. By doing a void survey, you can identify areas where these voids exist, and you can then fill it. You can put in piles, and you can essentially prevent the slab from sinking and cracking. Other voids are internal voids. Now, when pouring concrete, there's sometimes issues with concrete consolidation. And this happens for a number of reasons, but largely due to highly congested rebar. It doesn't allow the concrete to sink into the areas that it needs to. Or perhaps extreme temperature changes during the pouring, which obviously you guys on the East Coast and in the interior will know about. And this actually causes tiny voids to form, and sometimes a thing called honeycombing, which is essentially small little voids. And this can greatly reduce the structural integrity of the building. And then lastly, I just want to touch on something we've coined pre-design scanning. Now, the idea behind this is people spend a lot of money designing spaces, And those spaces, you may get there, you start scanning, and they can't go where they need to go. There's too many conduits in the way. So they spend more time, more money redesigning. And in doing so, you get back and you can't go there either. So this is the idea that why not scan the space, produce a CAD drawing of where everything exists, and then design your room based on that. In the long run, like, you save money doing it this way. And this is just a 3D walkthrough, essentially, of a site where we did this. You can see the top rebar in green, the bottom rebar in blue. Electrical cables running through the slab in red. These are slab bands running between the columns. You don't want to go through the slab bands. That's 3 times the thickness of the regular slab. And that's one thing that massively gets overlooked too, is just the location of the slab bands. You know, people spend all this time designing it and they don't think that there might be a slab band in the way. So it's a big problem. Lastly, concrete coring is something we offer in order to cut holes, core holes through concrete, and it goes hand in hand with the concrete scanning. And yeah, that is mostly what I want to say. If you guys have any questions, Gareth here will answer them and send them to me, and I'll answer them for you online. Thanks for listening.
Thanks, Mike. So there's been a few questions come through on the chat. First one from Timothy. How much space do you need to scan?
If you're just drawing like a hole, for example, typically a minimum of 2 by 2. So the bigger the better, but a minimum of a 2 by 2 feet.
Okay. One from Marcus here. Can you scan sandwich slabs?
You can, but you have to scan sandwich slabs from both sides. So sandwich slab, for those who don't know, you have a structural slab, and then you usually have a layer of insulation or foam, and then you usually have a topping slab. Now, the insulation or foam acts essentially like an air gap, and the radar speeds up, so you cannot see into that air gap. So you have to scan from both sides, and it's often misleading because people will scan a sandwich slab from the top, and they'll be like, oh, this is super easy. You know, there's one layer of rebar, job done. And in reality, that's not the case. You've got the topping slab, the insulation, and then a structural slab with who knows what in there. So you can scan them, but you have to hit them from below and make sure you can see all the way through that structural slab.
Okay, another one just came in. Can your Xradar scan water leak in the basement?
Water leaks. I would say no. If you've got a lot of heavy water in a slab, you can differentiate between, say, a very wet slab or not a wet slab, or if you've got a lot of water under a slab, that may be possible. But no, what you can do is determine if you do have an existing crack and you know where the crack is, you can determine how deep the crack goes and whether the crack goes all the way through the slab. And that may in turn determine if that crack is the source of your water leak. Now, you wouldn't use radar for that. You'd actually use ultrasound equipment, which is a whole other thing to get into. But so yes and no is your answer.
Okay, another one from Timothy here. Can you scan block wall?
Block wall can be scanned. Again, obviously the void space in the middle. You cannot see into the void space. So often we scan it in order to determine if it's been filled or not. If it's been filled, it's like scanning a regular wall. If it hasn't, then you have to sort of mark out the areas which haven't been filled. And if you want to core through that area, it's pretty simple. You core a hole and you just make sure you have a look before you continue coring. And that way you will avoid any conduits that may be running in that airspace, basically.
Okay, another one here. Can you scan a 3-foot slab?
3-foot slab? Again, it depends on what's in the slab and how old it is. For the most part, 3 foot is probably doable. It's probably at the limit of what you can do. But again, depends on the age. Remember that the older the slab, the better the radar is going to penetrate. If there's lots and lots of steel in the top and in the bottom, you're going to get limited. So it's probably at the limit of what you can do, but it is possible.
Okay, a question about reporting from Sam. How quickly can you turn around a report after a scan?
We send them out on site, basically. So you usually get it within an hour of us leaving the site, usually. Unless it's like a CAD report, then obviously that takes a few days. You have to go back and draft that up. But yeah.
Okay. Here's a question from Annie. Do we have to use grid system, or is that the most reliable system?
No. So grid systems are a method that has been used for a long time, but it is not the most applicable method for concrete scanning. Now, if you were to look for voids or corrosion or things like that, a grid system is the way to approach it. You're looking at an unknown quantity and area of something you're looking for. When you're concrete scanning for a core hole, a grid system is not a reliable method because you still have to put that information on the slab. And the problem is you need to attack the slab from multiple angles in order to see things. And if you're only collecting in, 90-degree angles, you're going to miss stuff. And it's proven to miss stuff. And I've been to many sites where people have previously done grid scanning and made a lot of mistakes, and they've hit stuff, and we've had to clean up the mess, essentially. So yeah.
Okay, I think that's it for questions. If you have any final questions, please type them into the box. Let's give you another minute or so. Oh, here's one, Mike. Can GPR scan through metallic objects or air gaps?
No. So as we said earlier, GPR will not go through metal. We have the ability to see past it to an extent, but if you have like a sheet metal, for example, a duct, you're not going to see through that sheet metal. Air gaps, as suggested earlier, no. The radar speeds up too quickly, so you don't necessarily see into the air gap. So hence the sandwich slab. Yeah, answer there.
Okay, then. Well, if there are no longer any more questions come through, I think that'll bring us to the conclusion. I'll hand it back over to Mike to finish it off.
Awesome. Well, thanks for listening. Hopefully you gained some knowledge. My email address is actually in the front. You're more than welcome to send me an email if you have any questions or give us a call. This webinar has actually been recorded, so I think Garrett's gonna send it out in case you guys missed the start or miss part of it or want to send it around. And yeah, have a great rest of your day.